Speech is a fundamental aspect of human communication. It allows us to convey not only information, but also emotions, intentions, and nuances. Automatic speech synthesis, also known as text-to-speech, bridges the gap between written text and spoken language, enabling machines to speak like humans. This technology has become increasingly important in human-computer interaction, impacting various aspects of our lives, from virtual assistants to assistive technologies. Imagine a world where computers could not only understand but also respond in a way that is indistinguishable from human speech. This is the promise of automatic speech synthesis. TTS systems take written text as input and convert it into audible speech, allowing machines to communicate with us in a more natural and engaging way. The applications of TTS are vast and continue to expand as the technology advances. From virtual assistants like Siri and Alexa to GPS navigation systems and screen readers for the visually impaired, TTS has become an integral part of our daily lives. As we move towards a future where human-computer interaction becomes increasingly seamless, the role of automatic speech synthesis will only become more significant. The journey of speech synthesis has been marked by continuous innovation and refinement. Over the decades, this field has seen remarkable transformations, each phase building upon the last to bring us closer to natural-sounding human-like speech. From the early days of rule-based systems to the current era of deep learning, the evolution of TTS reflects the broader advancements in artificial intelligence and natural language processing. Each technological leap has brought us closer to achieving more realistic and expressive synthetic speech. The early TTS systems were primarily rule-based, relying on a complex set of linguistic rules to generate speech. These systems were groundbreaking at the time, but they had their limitations. Early TTS systems were primarily rule-based, relying on a complex set of linguistic rules to generate speech. These rules dictated how phonemes, the basic units of sound in language, should be combined to form words and sentences. These rules dictated how phonemes, the basic units of sound in language, should be combined to form words and sentences. While these systems were able to produce intelligible speech, they often sounded robotic and lacked the naturalness of human speech. The quest for more natural-sounding speech led to the development of new techniques and technologies. The advent of statistical parametric synthesis marked a significant shift in TTS technology. These systems leveraged large datasets of speech recordings to learn the statistical properties of speech. By analyzing patterns in these datasets, statistical models could generate more natural-sounding speech compared to their rule-based counterparts. This was a major breakthrough, but the quest for even more human-like speech continued. However, the true revolution in speech synthesis came with the rise of deep learning. Deep learning models, with their ability to learn complex patterns from massive amounts of data, have enabled the development of TTS systems that can generate highly natural and expressive speech. Deep learning models, with their ability to learn complex patterns from massive amounts of data, have enabled the development of TTS systems that can generate highly natural and expressive speech. Today, these systems are capable of mimicking the nuances of human speech, including intonation, emotion, and rhythm, making them almost indistinguishable from real human voices. The earliest attempts at speech synthesis can be traced back to the 18th century, with mechanical devices designed to produce rudimentary speech sounds. However, it was not until the mid-20th century that electronic speech synthesis began to take shape. Rule-based synthesis, as the name suggests, relied on a set of meticulously crafted rules to generate speech. These rules, often formulated by linguists and phoneticians, governed various aspects of speech production, including phonetics, phonology, and prosody. Phonetic rules dictated the pronunciation of individual sounds, while phonological rules addressed sound changes in different contexts. Prosodic rules, on the other hand, dealt with aspects like intonation, rhythm, and stress, which contribute to the overall naturalness and expressiveness of speech. Building a rule-based TTS system was a laborious and time-consuming process. Linguists and engineers had to painstakingly codify their knowledge of language and speech, into a set of rules that could be understood and executed by a computer. Despite the challenges, rule-based systems played a crucial role in the development of speech synthesis, laying the foundation for future advancements. Deep learning, a powerful subfield of machine learning, has revolutionized many areas of artificial intelligence, and speech synthesis is no exception. This technology has brought about significant advancements, making synthetic speech sound more natural and human-like than ever before. Deep learning models, inspired by the structure and function of the human brain, are capable of learning intricate patterns from vast amounts of data. These models use layers of artificial neurons to process and analyze information, mimicking the way our brains work. In the context of TTS, these models can be trained on massive datasets of speech recordings, enabling them to learn the complex relationships between text and speech. This training process involves feeding the model with numerous examples of spoken language, allowing it to understand the nuances and variations in human speech. One of the pioneering deep learning architectures in speech synthesis is WaveNet, developed by DeepMind. WaveNet marked a significant leap forward in the field, setting new standards for the quality of synthetic speech. WaveNet uses a novel approach called dilated convolutional neural networks to model the raw waveform of speech. This innovative technique allows the model to capture long-range dependencies in the data, which are crucial for generating coherent and natural-sounding speech. This allows it to capture the fine-grained details of speech, resulting in highly natural and realistic synthetic voices. The ability to generate such detailed and accurate speech has numerous applications, from virtual assistants to automated customer service systems. Another breakthrough came with the introduction of Tacotron, developed by Google AI. Tacotron has further pushed the boundaries of what is possible in speech synthesis, offering a more streamlined and efficient approach. Tacotron is an end-to-end speech synthesis model that directly maps characters in text to a spectrogram, a visual representation of the frequencies in speech. This direct mapping simplifies the process and reduces the need for complex intermediate steps. This spectrogram is then converted to audible speech using a vocoder. The vocoder plays a crucial role in transforming the visual representation into sound, ensuring that the final output is clear and intelligible. Tacotron's ability to learn directly from text-speech pairs has simplified the TTS pipeline, making it easier to train and deploy high-quality TTS systems. This has opened up new possibilities for developers and researchers, enabling them to create more advanced and versatile speech synthesis applications. Fast speech, another notable deep learning model for TTS, focuses on improving the speed and efficiency of speech synthesis. By addressing the limitations of previous models, fast speech offers a faster and more reliable solution for generating synthetic speech. By predicting the duration of each phoneme in the input text, fast speech can generate speech significantly faster than traditional autoregressive models like Tacotron. This predictive capability allows for smoother and more natural-sounding speech, enhancing the overall user experience. This makes it well suited for applications where real-time or low-latency speech synthesis is crucial. Whether it's for live broadcasts, interactive voice response systems, or real-time translation services, fast speech provides the speed and accuracy needed to meet the demands of these applications. Prosody, often referred to as the music of speech, plays a vital role in conveying meaning, emotion, and intent. Imagine listening to someone speak in a monotone, devoid of any inflection or variation in pitch. The message might be clear, but the emotional impact would be lost. Prosodic features, such as pitch, loudness, rhythm, and pauses, add layers of meaning to our spoken words. They help us emphasize certain words or phrases, signal questions or statements, and convey our emotional state. For instance, a rising pitch at the end of a sentence typically indicates a question, while a falling pitch signals a statement. Similarly, speaking faster and louder might convey excitement or urgency, while a slower pace and softer volume could indicate sadness or fatigue. Understanding prosody is crucial for building natural-sounding TTS systems. Without proper prosodic modeling, synthetic speech can sound monotonous, robotic, and lacking in emotional expression. Accurately capturing and reproducing prosodic nuances is essential for making TTS systems more engaging, expressive, and human-like. Emotions color our speech, influencing not only what we say but also how we say it. The tone, pitch, and rhythm of our voice can convey a wide range of feelings, from joy and excitement to sadness and anger. When we're happy, our voices tend to be higher pitched and more animated. This vocal animation can make our speech sound more lively and engaging. When we're sad, our speech might become slower, softer, and lower in pitch. This change in vocal quality can make our words sound more somber and reflective. Conveying emotions through synthetic speech is a complex challenge that requires sophisticated modeling techniques. It's not just about replicating words, but also the emotional undertones that come with them. One approach to emotional prosody modeling is explicit prosody control. This method allows for precise adjustments to the speech's prosodic features. In this method, specific prosodic features such as pitch, duration, and energy are manipulated to convey different emotions. These adjustments can make synthetic speech sound more natural and emotionally expressive. For example, to synthesize happy speech, the pitch contour could be shifted upwards, making the voice sound more cheerful and lively. The duration of vowels could be lengthened, giving the speech a more relaxed and drawn-out quality. And the energy levels could be increased, adding more intensity and emphasis to the speech. Another approach is end-to-end learning, which simplifies the process by using a single model to handle everything. In this method, a deep learning model is trained to generate speech with the desired emotional expressions, learning from vast amounts of data. By training on a dataset of speech recordings paired with emotional labels, the model learns to map text and emotion to the corresponding acoustic features of speech. This allows for more nuanced and accurate emotional expression. The model learns to map text and emotion to the corresponding acoustic features of speech, creating a more authentic and emotionally resonant output. Style tokens offer a more flexible way to control emotional expression in TTS. These tokens act as cues for the model to generate speech in different emotional styles. These tokens, learned by the model during training, represent different speaking styles or emotional states. They provide a versatile tool for fine-tuning the emotional quality of synthetic speech. By providing the desired style token as input, users can easily control the emotional tone of the generated speech. The TTS system can then generate speech with the corresponding emotional expression, making interactions with AI more natural and engaging.